Ok. Boa tarde, pessoal. Sejam todos bem-vindos e bem-vindas a esse sexto seminário do ciclo internacional de seminários em materiais compósitos. Estamos caminhando aí para a reta final desse ciclo, né? Agradeço a presença de todos, a perseverança de muitos que estão aqui em todos os seminários. Lembrando que esse evento ele é realizado com o apoio da ABPOL, que é a Associação Brasileira de Polímeros, e também com a colaboração da MTS, Sistemas do Brasil, Texiglass, Instituto Senai de Inovação em Tecnologia e Engenharia de Polímeros. Não se esqueçam que a gente está monitorando a presença de vocês ali pelo chat, então, por favor, coloquem o nome e a instituição de vocês ali no chat. E aqueles que quiserem fazer perguntas, né, depois da apresentação, vocês podem acessar, ou durante a apresentação, podem acessar o Mentimeter por esse site que está aí na tela de vocês e inserir esse código, tá bem? First of all, I would like to thank you, Dr. Humberto and Dr. Saullo, for accepting our invitation. In my name, in the name of Associação Brasileira de Polímeros Regional Sul, it's a pleasure for us to receive you to give us this talk this afternoon. Thank you very much. Now, I pass the word to the chairman, Professor Sandro. Is with you.
Okay, thank you, André. Thanks a lot. So, I'm going to be hosting here today. First of all, I have to introduce our guests of the afternoon of this seminar. And the first one is Professor Saullo. Actually, today, for the first time, we have two, not one, but two. And they're going to share the presentation today. So, first one is Professor Saullo Castro, who is a materials engineer from the University of São Paulo, and who studied his master's in the Aeronautical Institute of Technology, ITA, on the topic of design and optimization of composite wing structures while working at Embraer. In the period between 2012 and 2014, he worked as a researcher in the 7th Framework European Project, DESICOS, while doing his PhD, from which he graduated from the TU Castro in December 2014. He's summa cum laude. Since June 2018, Saullo Castro worked as assistant professor in the group of Aerospace Structures and Computational Mechanics, ASCM, at Delft University of Technology, doing research in design, optimization, and analysis of thin-walled structures, dynamic analysis, deterministic and stochastic validation of full-scale models, and meshless methods for fluid structure interaction. So thanks a lot, Professor Saullo, for accepting our invitation to be here and give the seminar. And I'm going to introduce Professor Humberto Almeida, who obtained his PhD from PPG URGS in November 2016. He completed his first postdoctoral study at Leibniz Institute of Polymer Research, Dresden, in which he worked primarily with modeling, optimization, and manufacturing via tailored fiber placement of variable angle toe composite structures. Currently, he is a research fellow at Aalto University, Finland, where his work focuses on fiber-reinforced lattice and variable angle toe designs for composite structures. Humberto is currently a member of the editorial board of 5 journals, including section editor for Material Journal. He also serves as a regular reviewer for 60 journals. Humberto has published so far 34 peer-reviewed papers, 47 conference papers, and he has an H index of 15. His main research interests are on new methodologies to improve the mechanical performance of lightweight composite structures. So thank you also, Professor Humberto, for having accepted our invitation. It's a pleasure for us to have you both here. And I'm sure we're going to have a fine seminar, and I'm sure people will enjoy it very much. So please feel free to share your screen now and feel welcome from all of us here from ABPOL. Thank you.
Okay, thank you very much for this kind introduction. I'm going to start presenting, and we are going to dynamically switch between the two presenters. I think we had this arranged already. So the first slide is just a welcoming slide to all of you. Let's be. Yeah. Good evening from Delft. Despite in Brazil it's still 4 p.m. In Delft it's already 8 p.m. And Delft is an extremely beautiful city in the Netherlands, and we have now about 100,000 inhabitants. We are 11 kilometers away from The Hague, or in Brazil it's Haia. And in The Hague they have about 500,000 inhabitants, and we are 16 kilometers away from Rotterdam with about 600,000 inhabitants. The picture at the bottom, which is also my background picture, is a picture of our library. So our library has a very modern architecture. As you can see, it has grass on top of the roof. It's a very beautiful construction, and the two pictures above are pictures from the Delft city. TU Delft is ranked now as the 57th in the QS Global World Ranking of 2021. And we are ranked the top 5 among the top 5 universities in mechanical, aeronautical, and manufacturing engineering. Now going more to the faculty of aerospace engineering, we have in our bachelor's program of 3 years, about 450 new bachelor students per year. In our master's program of 2 years, we have about, oh, there is an echo somewhere. I think you could mute, please. And in our master's program of 2 years, we have about 1,262 master students in total. And now we have 181 PhD students and 237 academic staff members. This is where my office is located, where my pictures is in. Now I give the word to Humberto to introduce more about the Aalto University.
Yeah, thank you, Saullo. Thank you also, Professor Sandro, for the very nice introduction. And it's an honor to me to be here actually as an alumni of the Federal University of Rio Grande do Sul, in which I graduated from my PhD. And now, as Professor Sandro said, I am a research fellow here at Aalto University in Finland. And now officially greetings from Finland, very cold place, but despite the coldness, I must list a few.
Humberto, we lost your audio.
Sorry?
Yeah, now it's, there was a problem with your audio.
Okay, now, can you hear me now?
Yes.
Excellent, so, okay, so I will start over then. Can you hear me perfectly, correct?
Yes.
Okay, great. Okay, let me start over then. Professor Sandro, thank you very much for the kind invitation. Professor Sandro and Professor Andrea as well. It's a pleasure for me to be here today to speak a little bit of my research. And it's also an honor to me to speak as an alumni. I was supervised by Professor Sandro during my PhD studies. So thanks again for that. Let me now say greetings from the cold country of Finland, in which, despite of the coldness, I must list a few extraordinary facts here about Finland. In several rankings, we are well known as the happiest country in the world because of several factors. We promote pretty much equality without hierarchy. We have such an informal environment in our work, in our university. Finland is a very safe and clean, and also it's very well connected to nature. And although we are a little bit far away from the center of Europe, we have very good connections to move and to take flights to the main cities from Europe. Okay. Aalto University was founded in 2010, and although it has only 10 years of existence, there is already actually a strong background behind it, because Aalto University was funded after the merging of 3 other universities from Helsinki area. But despite we are only 10 years old, we are very proud to say that we are the 9th best young university in the world, and we are also the 50th most international university in the world. Just some key figures about the School of Engineering. Aalto University has produced, let's put it in this way, so far 3,300 students with 400 Master of Science degrees, 300 bachelor degrees, 45 Doctor of Science degrees. We currently have about 70 professors, and we are continuously look for funding from non-academic partners. Okay, that being said, and given this introduction, let me now jump quite a little bit about some concepts about variable stiffness composites. Variable stiffness composites emerged quite a while ago, to be precise, more or less 30 years ago, and it was invented by Professor José, who at that moment was a professor at Delft University of Technology, in which his idea was to replace conventional composites, as we can see in the figure here on the right-hand side, in which we have a straight fiber reinforcing the layer of a laminate, in which the main mechanisms of tailoring the properties of a fiber reinforced laminate is by changing the lamina angle of a particular layer and stacking them into a particular way that would meet the design requirements of a laminate under a particular load. However, with the appearance of modern manufacturing technologies, for example, automated fiber placement, which is so far the most well disseminated manufacturing technology for variable stiffness composites, it becomes possible to steer fibers within the plane of a laminate. As we can see on the right-hand side here, in another nomenclature, toe-steered composites, in which we no more have only one angle in a layer, but instead we can vary the angle in the plane of layer, and then we can even tailor more the property of laminate stacking plies with different angles within the layer and also out of the plane of the laminate. There are several nomenclatures after the first one, which was variable stiffness. With the appearance of several manufacturing technologies, researchers took the freedom to put the name that they judged to be the most suited for what they produced. For example, we have the variable angle toe composites, variable stiffness per se, toe-steered laminates, and also variable axial laminates. And some of them are, let's say, associated with the manufacturing technology associated with it. For example, variable axial is very well disseminated and correlated with tailored fiber placement process, which was invented at Leibniz Institute of Polymer Research in Dresden. And as we can see here at the bottom picture, we can clearly see the difference between a constant stiffness laminate and a variable stiffness one. Moving further on the manufacturing technologies to produce such laminates. Let me start and say quite a little bit about an automated fiber placement manufacturing process. It's a well-established process. It's largely used in most aerospace and aeronautical companies, such as Airbus, Boeing, and also NASA, as we can see in the video being played now. However, AFP is, as people in the industry say, it's well suited for today, but not for tomorrow, especially due to some key limitations, in which the most famous and the most critical one is the high deposition radius, or the minimum steering radius, it's the same. In which, for example, to produce a laminate nearly defect-free, let's say, we have a minimum steering radius of 500 millimeters, which kind of restricts the design freedom of a particular structure. Here is just some attempts that Saullo and I carried out here at a startup company at Aalto University, in which we gave some tries to steer fibers with AFP with several minimum steering radius. And as we can see here, we could only achieve a defect-free tow path with a minimum steering radius of 700 millimeters, which is quite a lot if we talk about aeronautical and aerospace components, and it restricts quite a lot as well the design freedom of the laminate. Based on that, on those limitations, some researchers from the University of Bristol invented in 2012 the continuous tow shearing manufacturing process, in which the main motivation was to overcome the limitations from AFP in order to avoid fiber wrinkling, resin rich areas, and also discontinuities. Here on the left-hand side, we can see the mechanisms to steer fibers with both AFP and CTS, in which, for example, with the same tow path, in AFP, we would have either gaps or overlaps, but with CTS, we can have a very smooth steering of the tow. At the center of the slide, we can also see the difference with the same tow path manufactured, or let's say simulated by AFP and CTS, and with CTS, we can get a pretty smooth tow path compared to AFP and nearly defect-free. Here we can see the potentiality to manufacture such structure, some small components with CTS. And also here comparing the minimum steering radius on the right-hand side with a minimum of 50 millimeters and 120 millimeters, we can get laminates with an excellent quality and defect-free. That's just a video that we received yesterday from a company called ICOMAT from the University of Bristol with the, let's say, the beta version of continuous tow shearing, which they are calling actually rapid tow shearing and not continuous tow shearing anymore, because it was pretty slow in the past and now it's extremely fast according to them. And they can also, as we can see in this video here, they can also manufacture laminates with a minimum steering radius of 50 millimeters and defect-free, which is excellent in terms of design freedom. The other manufacturing technique able to produce such composites is tailored fiber placement, as I mentioned previously, in which I have quite a lot of experience during my 3-year postdoc at Dresden, in which the best characteristic of this process is the very low steering radius, 5 millimeters, which is almost nothing. However, TFP has some limitations, especially because it only manufactures 2-dimensional laminates. So if you want to manufacture a 3D structure, you have to further infiltrate the resin through another process, for example, through infusion. And so it kind of restricts the spreadness of TFP. Also, several attempts have been carried out to manufacture such composites via 3D printing. As we can see here, some figures and some examples from an isoprint and mark-forged industries, in which they could manufacture a bracket located under a seat of an aircraft made of continuous carbon fiber filaments, some open hole specimens, some lattice structures as well. And also, as we can see here in this video, it's a bolted joint. This is the base layer composed of a unidirectional layer, and then the variable stiffness layer is placed on top of it, and they alternate with a quasi-isotropic laminate in which a 0-degree layer is replaced with a variable stiffness one. However, this technology is really far away to be mature. As we can see here, there are a lot of defects, and it's pretty tricky yet to manufacture such laminate, such complex laminate from 3D printing. At last, about the manufacturing processes, let me say quite a little bit about filament winding, in which there is absolutely nothing so far on variable stiffness laminates manufactured by filament winding. However, this is the most suitable process to produce pipelines and composite over rapid pressure vessels, especially due to the high productivity and high speed. We can see on the bottom of the slide a few examples on the aeronautical and aerospace companies. And yeah, I'll talk a little bit further in this presentation whether this technology can be or not suitable to produce such variable angle toe composites.
Thank you, Humberto. Now I'm going back to my presentation, explaining a bit more about the design of stiffened panels and design of unconventional structures as well. And the main focus of my research is the design, analysis, and optimization of thin-walled structures, either metallic structures, but the main challenges are always related to the composite structures. And my goal now is to make it clear for you why it is challenging to design correctly and to optimize composite structures, especially with variable angle stiffness. Okay. Consider this very simple example that I modified from Ready 2004. And in this example, we have a conventional laminate with only four layers. And you can see that the definition of the layers, if we assume that we have a constant thickness, the definition of the layers is given by these four angles defined by θ1, θ2, θ3, and θ4. And so therefore, in this design, this very simple design, we only have four design variables, and if we assume the thickness to be a constant. When we consider the manufacturing constraints for a straight fiber laminate like this one, the first one that comes to mind, and it's a very important one, is the maximum number of subsequent layers with the same orientation angle, what we also call the contiguity rule. And to prevent delamination, if you have too many layers with the same orientation, the laminate behavior becomes more prone to delamination during service. So the damage tolerance and yeah, if the crack propagation and the life of this composite structure will be reduced because of these bad design. So it is usual to avoid consecutive layers, and there is a rule of thumb that is we go up to 4 consecutive layers. Another common design constraint is the symmetry constraint, in the sense that if you want to keep the laminate to decouple the bend extension behavior. So when you extend the laminate, you don't want it to bend. If you want that to happen, you must keep your laminate symmetric. So that's a very common limitation, especially if you have laminates that are autoclaved. So because if you have laminates that are autoclaved and they are non-symmetric, during the curing process, there is a high tendency to bend and to warp the structure during the curing process. Another common constraint is what we call the balance constraint. And in this example, I have balance constraint with symmetry. And then that means that for each angle, I have to have a counter angle or a negative angle with the same magnitude in the opposite direction. And that is required if you want to decouple the extension shear behavior of your laminates. So if you don't have a balanced laminate, let's say you can imagine if you have a plate and all the fibers are oriented by 45 degrees, for example. When you extend this plate, the plate will have more stiffness in one direction than in the other, so it will shear as well. So usually we want to decouple this thing, this behavior. And there's another rule which is very common that's called the 10% rule or robustness rule. And we want that usually to have a minimal stiffness in all directions. That was well discussed in the work of Abdallah and Kasapoglu and Gurdau. Let's go now first, before we go for a variable stiffness Wingbox structure, I want to show already the challenge for a conventional Wingbox structures using only straight fiber laminates. This was an example I worked on for quite a lot back in 2009 during my master's, where I had a challenge to design a composite wing, doing simultaneously the sizing of the laminates of the whole wing structure and the positioning of the ribs and the angles of the ribs as well. And the design strategy by then was to subdivide the wing in different zones. And in this example, I have 7 zones starting from the wing root to the wing tip. And to keep the manufacturing constraints easy to handle, we always assumed that a zone that is closer to the wing root would require more reinforcement than a zone that is closer to the tip. And that makes sense if you consider the loading of a wing structure. We have a higher bending moments when we move from the tip towards the root. And therefore, we expect to have more reinforcements when we go to the root of the wing. So the design strategy was to use always when we move to a zone that is closer to the roots, just to add pliers and never to remove the layers. And the design variables, they are associated in this example with the number of layers for each orientation. And we allowed the laminates to be non-balanced. So we had a different number of layers in minus 45 degrees and plus 45 degrees. We only assumed the conventional angle, so 0, 45, and 90. But in some designs, we can also use any angle that we want. We will show some examples that we allow more angles than only these three. But when we use a small list of angles, like in this case, only 0, 45, and 90, we are usually looking at manufacturing processes that are simpler. For example, hand layup. And for hand layup, you don't want to have angles that are different than 0, 45, 90, or sometimes we have 30, 60, but not, for example, 53 degrees or 48 degrees. So for hand manufacturing, hand layup manufacturing, you should stick to more standard angles. In this case, by changing the level of each variable from 2 to 20 for the base laminate, which is the thicker one, and for the reinforcements from 0 to 5, we already reached a design space of 6.7 powered by 18 possible designs. And even if you use a method that can evaluate each design in only 0.1 second, it would take 21.2 billions of years to perform the exhaustive search. So that means you cannot do it. You cannot just evaluate every single design. And it tells you a very strong message that you need a robust optimization method. And looking at the size of the design space, the optimization method usually, in my experience, cannot be gradient-based only. Of course, the gradient-based methods, they are welcome to find local minima, but you need something other than that to perform a robust exploration of the design space. For conventional design, we can easily reach already this large design space, as I just demonstrated. And so can you imagine now a design where each layer, in my previous example, each layer was a constant layer with a constant angle. Now, can you imagine a design with curved toes like this one? So this was recently now submitted to the AIAA SciTech conference. And this is the result of an optimization with curved fibers. In each fiber here, let me just, there's something, can you see this green? I have no idea how this ended up here, but okay. So yeah, looking at one of these curved layers, we can see how the toes or how the fibers, they are varied throughout the plate. In this case, we have a linear interpolation of the angles along the width direction of the plate. And we start with 65 degrees, and in the middle of the plate here, we have 10 degrees, and then at the end, we have again 65 degrees. So it means we have 2 angle variables per layer. And another feature of this design is that this was designed to fit with the continuous toe shearing processes. And one feature here is that you cannot decouple the thickness from the steering angle. And that makes also the design space and the analysis methods much more difficult. And the number of layers is usually unknown prior to the design. And then it comes the challenge, even if you have a very good optimizer, how can you parameterize your design in a way that it becomes robust enough such that your optimizer can find an optimum that is a good optimum? It's always extremely hard to assume that you have found the global optimum. So I would just say a good optimum. So the parameterization must be good enough such that you find a good optimum. But if it's too, let's say, too open, your parameterization, you'll also end up creating a design space that is extremely large and extremely hard to explore. So parameterization, I would say, and so the design concept and how can you parameterize your design is a very key aspect for a successful structural design. And then, so moving a bit more back to from 2018 now, how did we start doing some parameterizations with the master students at ITA? And this was a work with Capasha, Hernandez, and myself. In this case, we subdivide or we mapped the wing box, in this case, the upper skin of the wing box, using control points. So that's a way to reduce the number of design variables. So instead of having one design variable per finite element or one design variable per region, we just have a set of control points. In this case, we have 9 control points. We control the design variables at these control points, and everywhere else, we have the properties of the structure being interpolated. And what from our experience, we had an improved design parameterization compared to the previous one, and allowed even more design freedom because we were not fixing the zones from or the transition zones from one laminate to the other. We are not fixing those regions. So it was found during the optimization. We had about 13 variables per control point. So we had this experience of a reduced design space. The optimizer could find a good optimum very rapidly using, in this case, also gradient-based methods. It led indeed to a more convex optimization using the lamination parameters, but it only supports this concept of using lamination parameters and the thickness completely decoupled from the lamination parameters. It only works well when you have a manufacturing process that decouples your thickness from your fiber steering. And as we discussed before, as Humberto showed, the toe shearing processes that are the ones that can deliver now with a high manufacturing rate and also a very small minimal radius. With those new processes, we cannot decouple the thickness from the fiber steering. So we need a better parameterization and a better optimizer than the one I'm showing now. And also retrieving the laminates, when we work with lamination parameters, retrieving the laminates, it becomes also quite a hurdle, especially if you have this coupling with the thickness. And also and on top of retrieving the laminates, you must retrieve the laminates for many regions, and then you must, in a way, do the blending between the different regions. And in my group, there is a person, Julien van Kampen. He's a very good specialist on doing blending of different regions. So if you want to know more, you should look for the work of Julien van Kampen. If you have trouble finding him, just send me an email. Now regarding the use of control points to define variable values, and in cases where we have a coupling between the thickness and the fiber steering, the most recent work was is being concluded this year. And in this case, we are no longer using the lamination parameters, but instead we are working again directly with the fiber angles. And then in a way, we understood, of course, that we have a much larger design space compared to the lamination parameters. But on the other hand, using the control points instead of the zones, as I showed before in the example of my masters, we could already reduce the design space compared to that work. And there is no need to retrieve the laminates. There is an automated compatibility between adjacent regions, and the possibility to couple the thickness with the steering. It allows us to perform optimizations using the most novel manufacturing processes. The only problem here is that still we don't have a very convex optimization. So if you use gradient-based methods only, you will fall into the first minimum from your starting point. What is this minimal steering radius that Humberto mentioned for AFP? That is a big limitation of AFP. And for CTS or continuous toe shearing, we go down to 50 millimeters only. And for tailored fiber placement, they go down to 5 millimeters only. But what is this steering radius? Consider this plate with the curved toes. If we take any coordinates on this plate, X and Y, if we measure the local fiber angle at that point, we can, using calculus, we can calculate the local radius of curvature. So just to remind you, for AFP, we are talking about a minimum range of 500 to 800. And we have to say, to go to 500, you need an extremely well-controlled process. It's very difficult to do that. For CTS, they can easily go down to 50 and TFP 5. And how to guarantee that all the toe steering in your optimization, you have to guarantee that the designs produced are respecting these manufacturing constraints. So how to do that? One of the approaches that we propose also this year, there are many others, I'm going to discuss some of them here. But one of the approaches is to measure this toe steering radius, or this curvature radius at the control points. So in this case, I have 9 control points on this segment of my stiffness panel. And if we look at this control point at T, or what we call the T13, and then we can calculate the local radius of curvature, and I'm calling this row 13. And if we go to the midpoint here, T22, we can also calculate the radius there, and so forth. So if you do this for all the control points, we can then guarantee that the interpolated radius of curvatures, they will be within the interpolated range. And how to calculate the radius? We use this formula from calculus, and where the variable that we need is dy dx. And if you remember, dy dx is the tangent of this local steering angle. Now, how does the steering radius look like? If you take a toe that goes from 0 to 38 and then back to 0, the steering radius is plotted here in the background. You can see that at the control point 0, 0, 0, and here at 1,500, at these coordinates, we have a minimal radius of 377. So let me pass one more. And at the inflection point, the radius go to infinity because the line becomes flat. And if we consider the steering radius, the minimum one that we achieved for this plate, we can conclude that this plate could only be manufactured using CTS or TFP. If we wanted to manufacture a design using AFP, we would have to constrain this radius to a higher level than we have now. Just to give you an example how these manufacturing constraints play a role on the design. And some literature here on how to include a minimal radius constraints in the optimization. Peters et al. In 2015 suggested to constrain the norm of the gradient of the fiber angle distribution. He used the gradient-based approaches, which are mesh dependent, so they calculated for each finite element or an average of the finite elements. And they applied for plates with cutouts. In the case of Quadros and Hernandez, they suggested another approach where they base everything on control points. It's also gradient-based, mesh independent, because now they are doing everything at the control points and not at the finite elements. And they also applied it to plates. And then we suggested this year to use the evaluation at an independent mesh grid, which can be the control points. And but we don't use gradient-based approaches. So that in that sense, if you are relying on gradient-based optimizers that are faster, then you might not want to use this approach. It's mesh independent. That's a good feature. It can be pointwise or averaged. And we applied it successfully for the design of plates and for the design of Wingbox skin panels. And an important remark here is that we managed to do this coupling the thickness with the steering angle, which is a very key design feature for the most modern manufacturing processes. Now to talk a bit more about design of variable angle filament-wound cylinders. There is a key, also a key feature, because there was an idea coming from the Federal University of Rio Grande do Sul, actually from the group of Professor Sandro Amico, and I think led by Humberto, and at that time, right, Humberto? And they had the idea to manufacture variable angle toe or variable angle filament-wound cylinders. And the original idea was to parameterize the design by subdividing the cylinder along the axial direction using constant angles. And this year, together with Jihua Wang leading the work and doing all the meta modeling, we proposed also more continuous designs or continuous parameterizations. And they proved at the end to give the best buckling performance. We are talking about a 20% improvement in the buckling load because of this higher continuity and the larger design freedom. If you want to know more, this work has been published already. You can easily find, if you look for our name and in Google Scholar, for example. So it's a very interesting designs that we ended up with. One of them is shown here. So this two toe paths, they represent the filament wound around the cylinders. And what we can see that we had closer to the edges, we had helical regions. So the plies they are more helically oriented. There is a transition region, and in the middle we have hoop oriented plies, and that also translates to higher thickness in the middle to improve the buckling behavior. If you want to know more, also please go there and check the publication. Now, going a bit on another very important aspect when we are performing a design is not only the parameterization of the design and the implementation of the design constraints, but also the analysis methods. The analysis methods, they are the ones that will tell if your design is respecting the defined constraints or not. So for example, you might have stress constraints or maximum displacement constraints. You might have also buckling constraints, vibration, natural frequency constraints, and so forth. The analysis methods, they are the tools, let's put it that way, the tools that will tell you if the design is good or not, given your constraints. I'm going to briefly talk about analytical methods, semi-analytical methods, and finite element methods. I'm not going into formulations here. It's more to give you an overview. So a bit more about analysis methods. So the idea is indeed to evaluate the performance of your composite parts as inputs for analysis methods. We are talking about the geometry, the loads that are going to act on your product, on your parts, the boundary conditions. These boundary conditions can be what are the adjacent structures of the structure being designed. Also, is this structure becoming in contact with another structure? Another thing is what are the elastic supports for this structure, and so forth. The laminate definitions, usually we're talking about the layers, the orientations, it can be constant or variable. These are all inputs for your analysis methods. And the outputs, we are usually talking about first strains and stresses. And from here we can derive failure criteria. Just to give you one example of a failure criteria that is largely used is the Hashing criterion from 1980. And where the Hashing criterion for laminated composite structures, it provides you with 4 failure modes: fiber tension, fiber compression, matrix tension, and matrix compression. So as you know, for fiber reinforced plastics or polymers, we have the failure can be either in the fiber, in the matrix, or in the interface. I think there is a modified version of the Hashing that also provides you a failure mode at the interface. And from knowing about your types of failure modes, you can then define what will be your design strategy. Are you going to consider a failure, a first ply failure, or are you going to consider a failure as a total failure of your laminates? If you're considering first ply failure, it becomes much more simpler to analyze. Let's put it like this: if you're considering a total failure, then it requires progressive damage models. Then I think about this if you want. For critical, now for non-local outputs, because strains and stresses, they are local outputs. Now there are also more global outputs that let's put it like this, that for example, critical stability loads or buckling loads and natural frequencies. These, they are not point properties of your structure. They depend on a larger consideration. So it can be the buckling load of a whole panel or even of a whole spar of a wing, or let's say a fuselage panel, etc. The natural frequencies, we can talk about the natural frequencies of just a single panel, or the natural frequency of a whole wing, or even of a whole aircraft, going more towards aircraft applications. These are again considered to be global responses. And this evaluation of the performance, it's where the question comes very strong. How to evaluate the performance? There are many different ways. And again, usually they can be classified as analytical, semi-analytical, and finite elements. So let's understand their differences and the main features. In an optimization, design and optimization process, we are always given the inputs, we evaluate the outputs, and then our optimizer, let's say, can change again the inputs to reevaluate the outputs. And the analysis methods, they are this box in the middle, providing you with the translation from inputs to outputs. In analytical methods, I always say it should be your first option. They are the fastest methods, the easiest to implement usually. But they have some limitations. Let's discuss them. So usually they are only defined or derived for continuous geometry. So there's rarely a method that works for structures with cutouts, especially if we're talking about buckling of structures, for example, with cutouts. It is quite hard to find a method that is robust enough, so you can rely on it, let's say, for your full design. If you have also abrupt changes, such as local reinforcements, the analytical methods, they tend not to work. It's ideal usually for simple geometries like square plates, rectangular plates, circular plates, shapes of revolution like cylinders or cones, things that can be easily mapped into a mathematical equation. Then for them, usually you can also derive an analytical method. And a very important feature of them is also that they are usually derived for constant stiffness. If there is variable stiffness, which is the topic of today's seminar, the analytical methods, they tend not to work. So at least you have to go for something more powerful. And that these, now let's say the next step of more powerful and robust methods, what I'm calling here the semi-analytical methods. Why are they semi-analytical? Let's try to make this clear now. They can be extremely fast, not as fast as an analytical method, I would say, but they can be as fast or comparably fast if they are well formulated and well implemented. And the last point, the well implemented part is also extremely key. And they work for a large range of geometries with cutouts, complex geometries that can come from an assembly of simpler geometries. And they work with constant or variable stiffness, and they are best applied when you can integrate the stiffness terms analytically. I'm not going into detail now. If you want to know more, please contact me. The nice thing about the semi-analytical methods compared to why are they faster? Why are they better? They are better than the finite element, which I'm going to discuss next, because they provide you a better approximation than a piecewise linear or piecewise polynomial approximation. Usually we use, let's say, approximations that are close to the exact solution, but we know at the same time that there might not be an exact solution, but we look for functions that tend to represent exactly the phenomena. And another feature that make them better than common, let's say, finite element method, or not better in the sense faster and converging with reduced computational cost, is that we include some of the physics kinematics into the stiffness calculation. If you want to see more examples on how this can be implemented, please go to my GitHub page. You can find some available codes there. And this is one example from the master's study of Janssens. He finished here at the end of last year, 2019. And he did a very nice example in his master's presentation that I took the liberty to reproduce here to explain a semi-analytical model. So consider this simple 1D beam where we want to calculate the deflection of this beam. So the beam is simply supported, as you can see, and there is a load at the position 2 here. So if we look at this beam, there is an analytical solution, which is given by the red line. And when we build a semi-analytical method for this, if we use just one term, for the approximation function, we would get a result like this, as you can see. So once we solve, let's say, the energy equations and we minimize the energy, the strain energy for this case, this would be, the blue line represents the best approximation that we can get with this interpolation function only using one term. Now, if we consider a second term, we can get an approximation that is slightly better. Let me go, I think something, yeah. Now with the second term, I can get an approximation that is slightly better. And this is again represented by this animation here. Now, if we keep including terms, I will eventually reach the same solution given by the analytical solution. So that's what I mean by using a nice approximation or better approximation functions than the ones that usually we find in finite elements. Now let's go to the next feature that I mentioned. In a general purpose finite element, if I wanted to simulate this conical shell, the strain equations, they are the ones given here usually. So I don't have any information about the cone geometry embedded into the strain equations. On the other hand, when we build a semi-analytical model, for the strain calculation, we already include the information about the local radius distribution, and in this case also some information about the semi-vertex angle of the conical structure. So we expect, since we are providing more information about the physics into the strain equations already, or kinematic equations, once we calculate the stiffness matrix, we are not calculating a general purpose stiffness, we are calculating the stiffness of a cone. So that's why they usually converge faster. And in finite elements, it is usually not always the slowest among the three solutions that I'm hearing comparing. They work for any geometry, so the advantages, and I largely use finite elements as well, it's because they use for any geometry. There are commercial, very good commercial software available. Also, there are many free libraries available that you can play with. They work for any stiffness distribution. And if you want to see a Python example that some of the students struggle with during our master's course, you can find it in this link here on my GitHub page. Some of the students that did this discipline with me now might be laughing. Optimization schemes for variable stiffness design. I think now, Humberto, if you want to proceed.
Yeah, sure. Yeah, thanks, Saullo. Let me now go further with speaking a little bit about optimization schemes for variable stiffness designs. I will kind of change the nomenclature now for variable angle toe, because it's the one we provided in the title. But yeah, anyway, when I talk about variable stiffness or variable angle toe, please have in mind that I'm talking about the same thing. Okay, very good. Let me talk firstly about genetic algorithm, which is a optimization scheme that particularly I have many good examples and many good improvements in terms of buckling loads, in terms of internal pressure strengths, external pressure strengths for composite structures with genetic algorithms. Let me just explain a few basic facts about it. It's very well known. And genetic algorithm is a statistical optimization process which initiates with an initial population, a random population, as we can see at the picture on the right-hand side here. We have initial design space with random individuals, which are stochastically and randomly oriented in a space. After that, they are distributed and they evolve based on a fitness function, which is the same of an objective function actually, but just the term is kind of associated with genetic algorithms, but they do pretty much the same thing. And then we have the generations, the selections of new individuals for the next generation, which is also based on the fitness. The crossover and the mutation between the genes. And then we have the next generation and so forth. As we can see here from the stochastic process after the initial evaluation of the randomly generated population. They are evaluated by the fitness function, and then we have the second generation here on the bottom right hand side of the slide. We have a different population which is already supposed to be better than the initial population, and it usually is. Otherwise, you would have to parameterize again your optimization process. And then we have a generation 3, which is also supposed to be better or to perform better than the previous generation, and so forth, until we reach the final generation, generation N, which is in which we have here at the center of the figure a convergent design space or a convergent optimal for your optimization scheme. That being said, let me also talk a few details about another optimization scheme, which is the so-called Krichin meta model, in which it's not actually an optimization method, but instead it's a meta model, in which a meta model is an approximation of the input and output of a function, and they are fitted to actually approximate the input to the output by training the meta model. Meta model is also known as model of the model, because when you have a model and you take some samples and then you train the samples based on the output that you have. So that's why it is also referred as the model of the model. It's very interesting because the Krichin meta model was originally developed for a totally different area, which is in the geostatistics. As we can see here on the bottom center of the slide. It was initially generated by the mining engineer Danny Krich, in which he wanted at that time to find the coordinates or the location of several points of a terrain based on measures that he knew and without the need to measure them again. As we can see here at this picture of a terrain, for example, he knows the exact location of this yellow point at the center of this circle, but he didn't know at the time the location of other points. So based on some interpolation functions and after the training procedure carried out with his method, he was able to find the exact or approximated locations of other points of the terrain. And then after successfully applying his technique for geostatistics and for those related areas, it was very rapidly increased and disseminated to other areas. And one of those areas is for composite materials, for example, in which there is quite a lot of research carried out in the last decade, or even a bit longer, applying Krichin meta model for approximating the response given from the input and the output of known values. Okay, then after a little bit of theory being said, let's now jump for some study cases. We are running a little bit out of time, but I will ask Professor Sandro and Andrea to give us some extra time. And I will now give the word to Saullo to speak about the first study case. So Saullo, yes, please be quick.
Thank you.
Otherwise I will not have the opportunity to talk about the other cases.
Okay, let's finally remove this from here. So yeah, thanks. Let's quickly go through this. So the first study case is a Wingbox design optimized for both AFP and CTS manufacturing constraints. This work will be published now in the SciTech conference. Basically, the first step consisted on translating the lift loads of the wing to panel loads, and then finally translating the panel loads or the panel representation to a representative, in this case, finite element model. We are using here a Nastran for the analysis. Then we parameterized the design using the control points, and since we wanted only steering along one direction, in this case the Y direction or the vertical direction, so all these constraints, they already come into play. And if we want continuity within one bay, so that means the the angles for this panel should be equal to the angle of the next panel or the adjacent segment of the panel. Then we also have this new constraint for those control points. And at the end, we have only two independent steering variables per layer for this parameterization. So these are called here T11 and T12. We ran a GA or genetic algorithm optimizer for this case, and we can see here 4 lines. So the black line represents a baseline optimization consisting of a straight fiber or an optimization consisting of straight fiber laminate in a laminate, in each of the laminates. And we reached the weight that is shown about 2.4 kilos for the whole panel for one bay. Then going to the CTS, or let's go now for the blue line, the AFP case 1. And the difference between case 1 and case 2 is that case 1 is for constant thickness, and case 2 allows also for variable thickness. And then we have this curve shown here, and the red line is the CTS, and also it goes about the same weight of the AFP and with the variable thickness. In this case, we realized that the minimal angle or the minimal radius constraint was not a limiting factor for the weight minimization. Therefore, using either AFP or CTS led us to a similar or comparable weight. And also what we can see here is that the CTS took longer to converge, and that's due to the larger design space. And just to give you an overview of how it would look like, so this is a sample of the skin using AFP. So we have here 8 layers given by plus minus. So I'm just showing plus or minus, not the counter angle. So not the balancing pair. And you can see a representation of these angles, how they would look like in the stacking sequence. And for the CTS, we have a much larger steering capability, and then you can see how the thickness also is building more prominently compared to the AFP result. And here we have a skin that would have at the end 10 layers. So now what would be the next step? And this is a work in progress. From the curved towpath, we generate CAD splines, and these are the same splines that were required to perform the AFP test that Humberto showed earlier. And then those splines, they go directly into the robot program that will perform the steering. Now let's quickly go to the second case, Humberto.
Yes, I will speak about now another example of a optimization using a genetic algorithm. I guess that most of you are continuously following this series of webinar, and the first one, I guess it was the first one, was given by Dr. Axel Spiekenheuer, who was my supervisor during my postdoc in Dresden. He probably mentioned about a brake booster structure, which is a boosting system of a bicycle, and basically the structure that sustains the brakes of a bicycle. And I'm extending a little bit further and covering a part of the research that was not mentioned by him, in which, as we knew, he showed the topology optimization of those structures, in which the initial design was a quasi-isotropic stacking sequence. You saw previously in this presentation how a quasi-isotropic stacking sequence looks like. It's composed by straight fibers oriented at 0, plus minus 45 and 90 degrees. And then it was topologically optimized. And then now we optimized it using a genetic algorithm in order to find the best number of truss sections located at each section of this brake booster, as we can see here. So basically, this is a scheme that was carried out to parameterize the boosting system, in which it was discretized the number of truss sections, or the number of trusses per sections, let's put it in this way. In which the initial population has a random number of trusses per section, as we can see here on the center of the slide. And then each chromosome is composed of 5 genes, in which a gene is basically a truss per section. And then the optimization has 12 chromosomes and 60 genes. Basically, it means that each section can have a maximum number of 5 trusses. So 12 sessions, we have 60 genes, as we can see here. The maximum number of 5 is not a random number, but instead it's actually defined by the maximum thickness in order to respect the design space provided by the topology optimization previously performed. Yeah, very well. We can see here on the top center of the slide a graph pretty much similar to the one that Saullo showed previously, which is the evaluation of the fitness function over the generations. And then we can see here that the optimum has been truly reached in this case. And then if we compare with the quasi-isotropic stacking sequence, we've got an improvement in terms of stiffness of 330%, and compared to the only topologically optimized brake booster, we've got an improvement in terms of stiffness of 22%, which was excellent, because previously the topologically optimized was considered the most optimal, let's say there, but we proved that with a good parameterization and optimization scheme, we could even go a little bit further. And it's not shown here because it was covered previously, but it was also validated experimentally, the improvement in terms of stiffness of this magnitude. I will now talk about another example, not using a genetic algorithm, but instead using an optimization, let's say an optimization scheme invented by our group, at a previous group at IPF, in which we optimized the open hole tensile specimen manufactured by tailored fiber placement, one of the manufacturing techniques that I mentioned at the beginning. The initial guess, let's put it this way, was with a laminate, a plate, for let's say, or a specimen, which is subjected to longitudinal tensile loading, and it is reinforced with rectilinear fibers oriented at the loading direction. And the loading direction is here indicated by the purple arrows. I should also mention that it was included a base material of ±45 degrees, which was an unwoven fabric. It is placed under the layer to be optimized, which is highlighted here with the black lines representing the fibers. And the main purpose of putting this ±45 layer was to prevent premature delamination during the longitudinal tensile loading, which is very well known to happen before the failure. Very well. Before optimizing it with our approach, we simply placed the fibers along the principal stress directions. We can see here that we no longer have only straight fibers on the design space, but instead we have some curved fibers, especially here around the hole. The optimization scheme developed is called DFPO, which is referred as direct fiber path optimization. And the fiber layout is shown here on the top left-hand side with fibers surrounding the hole, like very explicitly. So the design is pretty much different than the principal stresses. After the optimization, we also manufactured it. As I mentioned at the beginning, with tailored fiber placement, we need a further processing to make a laminate per se, because it's a dry manufacturing technology. So after we manufactured the preform, as you can see here on the top left-hand side, we have the preform, and then we manufacture it by infiltrating resin, which was in this case with vacuum-assisted resin transfer molding. We basically place the fibers here in the mold and infiltrate the resin assisted by vacuum. On the top right-hand side, we can see some properties, some physical characteristics of the laminates. we can see that the fiber volume fraction is pretty much similar, so that the properties that we get are pretty much weighted and comparable. Here on the bottom hand side, on the bottom left hand side, we see the quality of the manufactured laminates. It's of excellent quality. For those 4 specimens, the unnotched, the notched with straight fibers, the notched with principal stresses oriented, and the optimized sample. And later on, we carried out the tensile tests, in which the tests were assisted by digital image correlation in order to measure both strain and displacement fields of the specimen during the loading history. Here on the bottom right hand side, we can see a video of the tensile testing happening. Yeah, on the back of the slide, you can see Axel there, very curious, and now he was carried after the specimen was broken. So yeah. Very well. Here we can see some results at a glance. On the left hand side, this is the load strain curves, and on the top right hand side, the fractured specimens. And I like to highlight some fact about the fractured specimens, because in my point of view, when an optimization is successful, for example, for talking about this case for composite structures and composite laminates, the failure, in my point of view, has to be random. I mean, it has to be located at random places in the laminate. Because for the other 2 specimens, for the straight fiber reinforced design and for the principal stress design, the failure happened here at the net section, near the hole, as we see. But here, for the optimized specimen, we can see that the failure was pretty random, and it happened everywhere for the 7 specimens tested. Only one here, the specimen number 3, failed at the net section. The other one failed elsewhere in the laminate. So this is one fact that could let me know that the optimization was successful, let's say. Just summarizing the results, we've got improvements in terms of all properties analyzed, the ultimate load, the specific energy absorption, and specific stiffness, and also in terms of strength. Regarding the results from digital image correlation, this is also a result that I like a lot, and that I just mentioned about the stress concentrations around the holes, which is one of the key concerns when designing a component by fiber reinforced composites with discontinuities. And having a look here on the top right hand side and on the bottom left hand side, we see some stress concentrations around the holes. However, if we look at the bottom right hand side for the fully optimized specimen, we can see that there are no red areas around the hole. So basically we can infer that there are no stress concentrations and that they were alleviated with the layout provided by the optimization scheme. And I'll pass the word to Saullo to speak a bit about another example.
Thank you, Humberto. I'm going to go also quickly with these. This is a recent study that Jihua Wang was the first author. I think he's one of the attendees in today's seminar. So thank you, Jihua, for the nice work. And this is a nice picture showing more or less what we did. So the manufacturing was done at the University of Rio Grande do Sul in Brazil, where they for the first time, they manufactured variable angle filament-wound cylinders. Their steering, in this study, we discussed the 2 mechanisms of steering, and for this type of manufacturing, we are still unsure about the right steering mechanism for the filament, but this is investigation that we're carrying on now. And but in any case, the thickness calculation does not change. So the analysis models that we propose here, they work for either case, for toe bending or toe shearing. Then implementing the right toe kinematics allowed us to get to the right thickness pattern in the model, and also in these representations that we provided. For the optimizations, Jihua proposed an accelerated Krigi model, meta model, where the convergence is much faster than a usual Kriging method, and now he's applying this to even more difficult optimizations. But for this study, the idea was to maximize the buckling load. And as I previously showed, this is a typical design that we obtain. Again, I briefly go through this. We used the different parameterizations in the design, and the best ones, they were those based on continuous interpolation and control points. As we go quick through this because of time, just a bit more about the accelerated Kriging model. So the idea that the default Kriging model has an error estimator, and based on the error estimator of the whole interval of all design variables, it then proposes the next training point such that it is the mean square error of the whole approximation to the level that you want, to the tolerance that you want. And this is done continuously during the training of your Kriging model. And what Giro proposed is actually to have not only the new training point based on the full error estimator, but to have instead a let's say training window or a focused window or moving search window, as we call it, such that the search for the next training point can also be done in this searching window. And the searching window is moving because it changes from each iteration according to the optimum position that is found in the Kriging optimization. So in that way, we reached a much faster convergence, and then it enables, let's say, the usage of this Kriging meta modeling for much more complicated optimization problems involving many more variables. The optimal layouts that are shown here for different cases. This is an open access paper, so you can just Google and find it out and read more about it if you want. So just to show you a brief overview of all the different optimized results that we had. And the best ones, again, they were those where we used the continuous interpolation and by means of control points in the design. And again, the largest buckling improvement from the baseline was 20%, which is quite significant for these cylinders with only 4 layers. So we can extrapolate it for more layers. We would get even a better buckling improvement. I'll quickly go through this because of time constraints, and now Humberto will finalize with the last study case. Thank you.
Yeah, thank you, Saullo. This very last study case is pretty much similar to the previous one that was mentioned by Saullo, which is the variable angle filament-wound cylinders. But in this case, we move a little bit further from design, modeling, and optimization. But we also gave the very first trial in the literature to manufacture such variable angle toe structures by filament winding. So. Yeah, this figure pretty much summarizes what we did, which was carried out in collaboration with Professor Sandro and Saullo. We initially designed and optimized the cylinders according to the designs mentioned by Saullo. However, in this work, not all those designs were considered, but instead we only partitioned the cylinder into 2, 4, and 8 frames. The example we can see here at the screen is with 8 frames, in which we have a symmetry with the center of the cylinder. So although the cylinder is partitioned into 8 frames, we have 4 design variables instead of 8 in order to provide some symmetry. And then after the optimization, which was carried out with a genetic algorithm. So another example by applying genetic algorithm, it was for the first time manufactured by filament winding. And then we also prepared the specimen quite carefully by adding a resin potting on the edges of the specimens in order to alleviate the stresses when they are subjected to axial compression. So then they were also measured in terms of thickness imperfections, which was carried out with digital image correlation. And then they were subsequently tested in uniaxial compression with tests also assisted by DIC. As I previously mentioned, it's the first time that a variable angle filament-wound composite is manufactured by filament winding, in which the main idea was actually to combine the design freedom of a variable angle toe configuration with the suitability of filament winding to produce such kind of a three-dimensional structure. In this case, it is a cylinder, but it could be, for example, a composite of a rapid pressure vessel. The innovative designs was previously mentioned by Saullo, so I don't need to go too much into details here. The fitness function, which is also an objective function, as I mentioned, was to maximize the buckling load, the first buckling load of the structure. We can see here a quick video of manufacturing this cylinder. But now there is a question arose after the last slide that Saullo mentioned for those layouts with a higher continuity among frames, in which is it possible to manufacture such configurations with a high thickness buildup at the center of the laminate? Is it or not? We still don't know. We don't have the answer for that. But in order to provide them a proper answer, we have been recently granted with a collaborative project between FAPEX and FAPESP, which are funding companies from Rio Grande do Sul and São Paulo. And we'll see in the following months whether those optimum layouts will be possible or not to be manufactured. Okay, moving a little bit further, we also provide here how the specimens are prepared for tests, because having a look on the left-hand side, on the top left-hand side, this is the as manufactured cylinder. We can see that the edges are, let's say, they have the same thickness of the whole shell. And if we test this structure here, we will most likely have a lot of troubles when they are uniaxially compressed, because we will have a lot of concentrations of stress on the edges. So for that, we carried out a casting in which we added a 15 per 15 millimeters casting areas here on both edges of the cylinder, and then at the end we achieve this final prepared test cylinder for testing on the right hand side of the slide. On the bottom right hand side, we can see the prepared specimens for the four families here in considered, in which it is on the left side of this figure the specimen wound with a minimal angle, and then with constant stiffness, and then both variable angle toe, in which the structure is divided into 4 frames and into 8 frames. As I mentioned, the tests were assisted by DIC as well. We can see here a schematic representation of the tests, which was carried out at TU Delft. And the results were actually excellent, better than we expected, because we've got extreme high improvements in terms of ultimate load. Having a look at the load displacement curves here, we can see on the graph D for the variable angle filament wound cylinder with 8 frames that we got substantial improvements in terms of the maximum supported load by the cylinder. And looking at the thickness pattern, the thickness imperfection pattern of the cylinders on the right hand side, we can see that the thickness is quite constant for all configurations. So for example, although the optimization was not, for example, weighted by the mass itself is not very determinant in this case here. We can see here some very interesting color maps provided by DIC. We can see here on the first row the axial displacement, and then the radial displacement, the axial strain and the von Mises strain. These color maps are very interesting because we can see throughout the loading history the buckling mechanisms and the stress mechanisms and strain mechanisms as well acting onto the shell, and then we can reach pretty much very well conclusions based on these experimental observations by DIC. The four variables here in observed are quite similar for the minimal angle, constant stiffness, and the cylinder with 4 frames. They look pretty much the same. However, when we have a very high degree of steering for the cylinder with 8 frames, we have pretty well different displacement and strain maps for the cylinder. Yes, so sorry for that. I have to run a little bit because we kind of extrapolated the time. But yes, so let me thank Professor Sandro and André for giving us the opportunity to talk a little bit about our research. And then if you have any questions, I'm more than happy to answer.
Yeah, thank you all. Thank you, Professor Sandro. Thank you, André.
Okay, thank you. That was a very nice seminar, a lot of content there. And I do have some questions, and I'm gonna try to quickly go through them. I'm gonna start with Humberto. Humberto, I have got 2 questions here for you, actually 3 now. So the first one is anything on maintenance of DS panels. For instance, how are patch repairs conducted in DS panels? Can a constant stiffness patch be used to repair a panel or DS panel? What can you tell us about repair?
I think perhaps I can step into that.
Yeah.
So for the panels with as we designed in the work with Machado and myself, so we were repeating the pattern of the variable stiffness pattern throughout the bay of one panel. So in that case, it's more modular. So you can define a repair patch that would have the stiffness for that region. But I know that from experience also that if you want the maximal or the best optimized structure, you should go a bit away from the modularity, but then you will penalize on the maintenance later. So it's always a trade-off between if it's more modular, it's easier to repair, but then you are penalizing your design. Yeah, so the answer is yes, it can be designed for better maintenance, but it will not be the best design, of course.
Exactly. I cannot hear you anymore.
Okay, someone is muting me. What criteria for selecting the control points in the design parameterization?
For what example?
I think was right in the beginning, one of the first examples there. I think was Saullo.
The first example was Saullo's, yeah, for the Wingbox.
So the question is how to set up the control points?
Yes, how to select, yes.
Okay, so that's a good question. If you can quickly go back there. The number of control points, it defines not only the discretization of let's say of the design space, but if you want, it can also discretize the interpolation order. So let's say in this case, we have a 3x3 control points. So we will achieve second order interpolation for angles. So if you think that you are always, if you use this interpolation and then you feel that you are never reaching the minimal radius constraint, it's a sign that you can add more control points to have a higher order interpolation, and this higher order interpolation will lead you to smaller interpolation angles. So the advice is start with less control points. If you reach the minimal steering angle, or if you don't reach the minimal steering angle, then it's a sign that you need more control points that will allow you a higher order interpolation to reach the minimal steering angle. Yeah.
I think it's gonna be helpful for someone who wants to start with this subject. Yes, thank you. That actually was a question of Mateus Madrid, and he has another question here.
Expected.
Yeah, another question here is, in wing panels, is the objective of optimization to minimize compliance?
Yeah, that depends. So the minimize compliance means stiffness. Yeah. So that really depends. I think like the right airplane design, we're looking at minimal fuel consumption. So it might, if you consider the airplane as a whole, the novel designs, they are based on, let's say, what is the minimum fuel consumption for a given airplane mission. So this multidisciplinary optimization might not even lead you to the most lightweight design. But let's say the compliance requirements, so minimum compliance or maximum stiffness requirements for Wingbox design, they are strictly related to the bending frequency, or the bending natural frequency, and the torsion natural frequency, and how they change with the speed of the aircraft. So if there is coupling between, or if these frequencies get close, then we have what's called a flutter, static flutter. Yeah, so you want to avoid that. So it's not really maximizing or minimizing the stiffness. It's more trying to avoid this coupling between bending stiffness and torsion stiffness, yeah, in a way. Okay.
All right. Another one here is about cases 4 and 5. If hashing failure was used in the FE analysis, was the hashing used in all analysis?
In one of my cases, actually, for the open hole plate, hashing was used, but maybe he's actually asking about one slide that Saullo presented that he mentioned about hashing.
I think it's for the cylinders, right? For the case 4 and 5.
Yeah.
For the cylinder now.
For the cylinders, they were constrained by buckling.
Yeah, it was only buckling.
But
after failure was considered in the optimization.
Yeah.
I noticed also, Saullo, that you talked about hashing failure criteria in your part there. Is there any particular reason that you're choosing hashing, or could you suggest another failure criteria?
Yeah, I know about the PUC criterion, which is, I think it's taking more place now over the hashing criterion. But I used the hashing for the designs I did in my PhD. We tested, in that case, we were designing cylinders that could undergo 50 times buckling without failure. And the hashing was very good. We could avoid failure after buckling, and but I know that there are better failure criteria now.
Yeah, I can kind of complement this answer, because the main limitation of the spread of PUC is that to identify the parameters is extremely hard. So people really run away from PUC when they have to model and to optimize considering PUC parameters. So as optimizers and designers, we try to calibrate the optimization and the modeling parameters as better as we can. And for PUC, this is nearly impossible. So usually they run away from PUC and they go, for example, for hashing, because it's easier to identify the failure criteria parameters. For example, just carrying out tensile, compression, and shear tests. And for PUC, you have to do a bunch of other tests.
Do you think for variable stiffness plates, the characterization to get the right PUC parameters is even harder, or it's about the same?
It's much harder. It's much harder. That's why you nearly see an example of optimization considering PUC failure criteria.
Okay, fine. I've got another one on Wingbox. It's complementary to that, the last one. The objective function there is mass of wing or displacement, or end displacement.
Oh, that was the mass. That case was the mass. If we want to include the displacement, it goes not as an objective. Usually it goes as an extra constraint.
Okay. All right. Another one here is, has there been any investigation into the performance of VS panels on impact?
Oh, that's a very good question. Yeah, I think actually that's a great question, especially not only impact, but let's say compressive behavior after low speed impact. I think.
Yeah, compression after impact. Yeah.
Okay, so from that, if you go back to the beginning of the presentation, let me try to very quickly go there.
Yeah, but initially the answer is no.
No, but if you go, if you go to AFP designs, where you have this resin-rich areas, can you see my slide here?
Yeah. Yes.
With the AFP, like using cut and restarts, you have these resin-rich areas, and so they indicate there will be something happening there if there is a low-speed impact with regards to crack initiation. So I would expect the compression after impact behavior to be of a lower quality than a straight fiber laminate. On the other hand, look at the CTS. It does not produce this resin-rich area. So I would say I would expect for AFP with cut and restart, yes, it will be worse, or it would be quite worsened the fact that you have the steered fibers. But for the CTS, I don't know. No. That would be my answer, but I don't know if it fully agrees with that. But
okay. There is one here now for, I think it's Humberto. How is variable stiffness better than the conventional filament winding method, especially for an internally pressurized cylinder, since the loads are not very much?
Yeah, for internally pressurized cylinder, we don't have the answer yet, but for uniaxially compressed, we could, Saullo, if we could go to that one of the last slide with the.
Let me go quickly there.
With the table, I guess it's better if you go. We've got an improvement in terms of a ultimate load of 70% for the maximum supported load with the variable stiffness configuration. But for internal pressure strength, we can certainly get improvements, especially because we have a more room for improvement for the internal pressure strength, and the experimental test is also easy to carry out. But unfortunately, I cannot give you the answer now. So in a few months, maybe. Let's hope so.
Okay. All right. I did all the questions that were previously here, but now I have 4 more. So I think I'm gonna.
It's okay. It's okay. Let's go.
I'm gonna do at least 2 more. Okay. Just to. Okay. So the next one is 3D printed continuous composite have been growing significantly in the past year. It seems that the 3D printed structures could achieve even stiffer structures near optimum.
I would say that so far, no, because, for example, I have a 3D printer at my facilities at Aalto from an isoprint, and I have been struggling for many months to produce the high quality laminates, even without holes and discontinuities. We've got a lot of resin pockets and a lot of fiber deviation. So my answer is, it is not mature yet if we compare to, for example, TFP and CTS, but I would say that in the next few years it will become one of the best technologies to produce high quality composites.
If I may step in, I know there is a colleague here, Kunal Masania. He's a really high specialist on 3D printing. Kunal, if you want to add anything with regards to this, please step in.
Yeah, I think Humberto is right. I think the technology is not quite there yet. The biggest problem is that you need to introduce a post-consolidation step to get the voids to be skipping away. So I think the big innovation will come when somebody can make composites without voids in the object, or printing in 3D. So you can keep an eye out for our work on that.
Thanks.
Okay. So the last question, thank you, Saullo. I noticed that you did your master while working at Embraer. Do you have any collaboration now with Embraer? Have you had any collaboration with Embraer after you left?
I don't have a project with Embraer, but I do have collaboration with Embraer. I have many colleagues working there that we are doing research together, but without a formal project. Yeah.
Okay. All right. Sorry, guys, we don't have more time. Andrea is already there, so I think we're going to have to end this. That's been quite a pleasure to have you here. That was quite a nice seminar, and I thank you again for having accepted the invitation.
Yeah.
And I need to pass to Andrea now. Thank you again.
Thank you for the invitation again. Yeah.
Thank you as well. Yeah.
Okay, thank you guys.
Just if you have any questions from the audience and you do not have time to ask here, please send me an email. I would be happy to answer.
Same to me. Same to me. Yeah.
Thank you.
Okay. Thank you very much. Sorry to close the time, but we need to respect the time.
Yeah, of course. Let's do that.
Thank you again. It's a very interesting talk. I appreciate very much. Bom, pessoal, para vocês que acompanharam até agora, eu agradeço. Lembrando que a todos aqueles que assistiram 4 do seminário já recebem um certificado, mas não deixem de acompanhar com a gente na próxima semana o último seminário do ciclo, tá? A partir de segunda, a gente vai estar divulgando para vocês na página do Facebook e também no nosso LinkedIn. Desejo a vocês todos um bom resto de dia, se cuidem, fiquem bem. Um grande abraço, tchau, tchau.
Abraço, tchau,
Valeu.
tchau.
Tchau, pessoal.
Falou.